Okay, so this is what we're going to talk about today. We're talking about acid-base neutralization and titration. So which one right on this board today? Let's see if that works better. Okay, so we're going to talk about predicting products of a neutralization reaction. Good morning. And then we're also going to talk for a minute about titration. Lab 13 is on titration. So we'll talk more about titration when we talk about lab 13. So that's at the end of the very beginning of March, we'll do a titration. And then we're going to determine the volume of base needed to titrate given a mass of acid. So that's one of the Alex topics. So the first Alex topic is this first one, predict the product of a neutralization reaction, and then we'll talk about calculation for a titration. And you will have to do a titration calculation problem in lab 13 also. So a neutralization reaction is just where we're talking about acid-base neutralization, so where we add acid to base and they cancel each other out. So the products of an acid-base neutralization reaction always produces water and salt. Okay, that's always the products. So on the Alex question, when it asks you, what are the products of this reaction, and you have an acid plus a base, you should always at least put water. Okay, that's the easy one to remember. Put water down. And then the other part is a little bit tricky. You're trying to figure out what we end up with. So let's turn on the pen. Let's see. Okay, so here the water comes from the hydrogen ion. Oops. Our hydrogen ion here and the hydroxide. So together, those make water. Okay. So remember, our acid splits into H plus and A minus. So we have our proton and our conjugate base. The base is going to split into the metal cation and the hydroxide. And then the H plus OH, that gives us this water. Okay, so then we cancel this out. That's gone, that formed water. Okay, and then the conjugate base, so whatever the conjugate base is, and the metal cation form this ionic compound. So we got a metal and some conjugate base. That's our salt. Okay, so right now this has a +1 charge, and this one has a -1 charge, so we just need one of each to go together. Okay, so we can predict the salt based on our metal and our conjugate base. Okay, let's see. So let's look at one, like a real life one. So pretty common one is hydrochloric acid. This is the titration that we did in just regular chemistry. We added hydrochloric acid and sodium hydroxide. Oops, I don't want that. And we end up with, so we're always going to end up with water. And we're always going to end up with, so the hydroxide is gone, and the hydrogen is gone, just the hydrogen here. And then the whole conjugate base becomes part of the salt. So the sodium is in the front, so we have to write the sodium first. Also, we know that metals go first in the formula. So we can either look and say, oh, it's in the front, it needs to go in the front. Or we remember it's a cation, and then chlorine is also, oops. Oh, I don't know why it's doing that. Nope. So chlorine is second over here. It's also an anion, so it goes second. So that's how we know that. The other thing that we need to do is we need to check the charges. So sodium has a +1 charge. Chlorine has a negative charge, so we just need one of each. So this is a balanced reaction, or balanced formula. And then we do need to go back and balance the chemical reaction. So we have one sodium, one chlorine, 2 hydrogens, 1 oxygen, 1 oxygen. So it's balanced. Okay. All right, so I want you guys to try these two. try to predict the products. We have an acid and a base, and down there we have an acid and a base. Try to figure out what we would end up with.
To balance it out. I know it makes MgCl and then
I'm just being very excited. You figure it out. I'll ask questions like, yeah, I didn't know. Is it because it's in my arm? It's MgCl2.
I just know I mean, two.
Yeah, I think it's
Oh, yeah.
Yeah, okay, I just mixed them up.
All right, how are we doing? Are we ready, or do you need a minute? Where are we?
Finish the first one.
We finished the first one? Okay. Okay, do you want to go over it, or do you want to keep doing
I
it?
think we have to do this one.
Do you do the second one? Okay.
Sorry. See, I don't want
I usually get large. If you want, yeah. I would do some. Okay, yeah. Thank you.
Oh, yeah.
Does it matter the order of the products?
It does. Oh, you mean like this water or the salt first? No.
Okay.
No. The order of the metal and the conjugate base matters. Like you can't put it can't be hydroxide sodium.
Okay, yeah.
But yeah, you can put the salt first, that's fine.
Yeah.
I just like to write water first because it's easy.
Yeah,
I did it out of the way.
And then I got it.
Oh, okay.
So I just did
You're
now.
just checking, okay. All right, how are we? Are we ready to go over it? Do we need a minute? You guys are still discussing?
No, because you also have two of the HCl to balance out the equations, and then there would be two waters and then two CLOs. I forgot how I did this. CaClO.
Yeah. Oh, yeah. That's right.
So you just balance it out.
Yeah.
Okay, I think I'm hearing your conversation closing. Let's go ahead and we'll talk about this. All right, so what are our products here?
H2O.
Good, so we're always gonna get water, so always write water. Okay, what else are we gonna get? Metal goes first, yes. MgCl2, good. And you checked the charges, good. MgCl2. So Mg, we should check the charge. Mg has a 2+ charge. Cl has a minus charge. So when we crisscross, we need 2 Cls for 1 magnesium. So this is our formula. Don't write the charges. This is like showing our work. Don't write the charges in the formula. Okay. Let's see. So the water came from hydroxide and hydrogen, and then magnesium came from Mg and Cl. Okay, then we need to balance this. We have 2 Cls over here, so I'm going to put a 2 in front of the HCl. Where's my mouse? There it is. So I'm going to put a 2 here. So now I have 2 Cls, 2 Cls. I also have, how many hydrogen? I have 4 hydrogens. 2, 2, and I have 2 oxygens. So I need to put a 2 here. That will give me 4 hydrogens and 2 oxygens. You're doing all right so far? Okay, good. All right, this one, we're also going to get water. And what is our other product? This one was tricky for 4th period. What's our other product?
CaCl.
Good. CaClO4. And then, how many of those do we need? 2. We need 2. So if you don't remember the charge on an ion, we can look over here. What's the charge on hydrogen? +1. Good. What's the charge? So that means this other thing, that the conjugate base has to have a minus charge so that they cancel out. So that can help us figure out the charge. We have 1 hydrogen, that needs to balance the charge. Okay, now we need to balance our chemical reaction. So what should we do? Yes, there does need to be 2 H2Os. There also needs to be a 2 in front of this because we have 2 ClO4s, we need 2 ClO4s. So the problem, I'm just going to tell you that, so you guys didn't do this, but the other class, they were trying to break the oxygens off of the conjugate base. The oxygens stay in the conjugate base. Does that make sense? So just like you did it right. Don't try to pull these oxygens off and make them into water. So this is a covalent, this perchlorate, ClO4, is covalent, so you can't pull those oxygens off. They're not going to form water. Does that make sense? Okay, so don't do that. Watch out for that. That will show up in Alex. Okay, questions on this? Do you feel like you can do this? So okay, you can predict products and balance. Okay. All right, so when we add an acid and a base, that is also called a neutralization reaction because the acid and the base are canceling each other out. So we start with something acidic, we start with something basic, we end up with water and salt. Both of those are neutral, so that's why it's a neutralization reaction. So our goal of a titration is to figure out, we have a really precise knowledge of our base or our acid. So our titration will be a base titration. We're going to use a really precise amount of base to figure out exactly how many moles of acid we have. And we can figure this out when the amount of acid is equal to the amount of base that we have. Okay, so what the key here is that we have an acid is neutralized and we have exactly the same amount of acid, moles of acid as we do of base. Okay. And we use an indicator to tell us when the moles of acid equal the moles of base. And so when that's true, when we have equal amounts of acid and base, that's called the end point of our titration. Okay. So what you're going to do on lab 13 is you are going to titrate vinegar. You're going to see the concentration of acetic acid in vinegar. So some of us are writing notes. If you're not writing notes, I want you to look up for a minute. Look up, where do we use titrations in real life? Like, who uses a titration? What kind of job can I get when I use a titration? I don't know if Indeed is blocked on your Chromebooks, but you can also look up Indeed and like search titration and see if there's any jobs that are open that use titration. Okay, food industry, does it say like what they're using it for? Like what are they looking for? We're gonna look for moles of acid, the concentration of acid.
It just says, determine the quantity of the reaction.
Okay, so they're just figuring out how much of something. So this is called a quantitative technique. We're trying to find the number of something. We're not just trying to find, oh, what color is it? did something happen? So you want to actually know a value. That's quantitative chemistry. Okay, anyone else find anything else? Find any jobs that use titration?
Chemical manufacturing.
Okay, is there any like nearby? Could you get a job doing this? In Utah, yeah. Or nearby?
I don't know, I could look for it.
Okay. I just think this is interesting. This is like a skill that people actually use. We're like actually doing something that people use in everyday jobs. Okay. Well, keep that in mind. I think this is kind of interesting. I have used titration before. I did this in my research. So this is these are all people that I've worked with. This was my PhD advisor, this person here, Joseph Hupp. And so these people wrote a paper on titrating a material. So the material that we worked with a lot had these zirconium oxide spots in it. And they figured out that, this person, Rachel Klepp, she figured out that you could titrate this material. And based on the curves that the titration made, you can figure out what kind of groups you have. So you have hydroxide groups, you have water groups attached here. So depending on your material, you can figure out how many of each type it has. And then we cared a lot about sticking stuff onto this material. So we can figure out how many we could stick out onto our material based on the this titration. So we had an auto titrator. I never used what you're going to use. You're going to use a burette. So I imagine that if you're doing this in industry, you would use an auto titrator. So you like understand all the basic principles, but then this machine does it for you. So if your company has to do a lot of these, they're not going to have you do that. Waste your time and do this. You can set up like 20 of these and then go do something else. Okay, so that is an auto titrator and a different application. So what we're going to do is the old-fashioned way. We're going to use a burette. You have used a burette before. We figure out how much initially we have. We figure out how much we use by subtracting the final reading from the initial reading. We'll use our Erlenmeyer flask, and then we talked about, just briefly, we use an indicator. That indicator turns pink when it's a little bit basic. It turns pink in the presence of base. So when we have almost equal acid and base, then our solution will turn pink, and we'll know that we have reached our endpoint. We'll have equal amounts of acid and base at that point. And we'll talk more about this when we do our lab 13. Okay, so this is our process for our Alex questions. We are going to first write and balance the chemical equation for the acid they give us. So they'll give us an acid. I think every time we're going to add sodium hydroxide. And then we know that we'll always get water and then some kind of salt. And then we need to balance this. So this is going to, by balancing out this reaction, we will know how many moles of base we need for every mole of acid that we add. And there's a few different ways to do this first step. We can balance it, or we can just look at the acid. We're going to just do the very formal way of this, doing this equation, this problem. And then if you can find some shortcuts, that's fine. So once we have our balanced equation, we're going to calculate the number of moles of acid that we use. So we just take the, let me write this down, we're going to take the mass. Oops. And then we're going to divide by the molar mass. Oops. Okay, and then based on our mole ratio, well, based on how many moles of base we need for acid, we can figure out how much hydroxide we need. And then we'll take, so then we'll have moles of hydroxide. And then we're going to use the moles, the molarity of the base to calculate the bond. So they're going to give us the molarity. We'll have the moles. So N is moles. We'll have the concentration. We'll do moles divided by concentration to get volume. So it's, it looks like a lot of steps. So it's not too bad. So this is our last alexandrin stuff we need to cover. Thanks. Okay, I think we're good. All right, so this one we have 0.0791 grams of citric acid, and it tells us that it's a triprotic acid. What does triprotic mean? It can give away 3 protons. So if we look here, in the front of citric acid, we have 3 protons. I just kind of crossed it out. So we get 3 protons. Triprotic, 3 protons. It's added to a volumetric flask and diluted to a volume of 250 milliliters. This is, we don't need this, okay? The volume of the acid. Okay, they're trying to trick you. We don't need that, okay? So cross it out. The sample will be titrated with 0.1800 molar sodium hydroxide. So we need this and we need this mass. So the first step is we're going to balance our chemical equation. So we have our acid H3C6, H8O7. And then we're going to add sodium hydroxide. So we have our acid and our base. So it's a titration, an acid-base titration. And then what do we always get when we add acid and base? Good, water and salt, some kind of ionic compound. So here, this is our conjugate base, like this thingy right here. So I'm going to get Na. What's the charge on Na? Yes, +1. Thank you. What's the charge on? Oh, it's on click. What is the charge on the other thing? So it's not -1. Let's see. Oh, I have to present. So look over here. We have 3 hydrogens. Hydrogen each has +1, right? So there's 3 of those. So this is the 3+ charge. So what does this have to be to balance it? Good, this has to be 3-. So we need 3 sodiums for 1 of these conjugate bases. Citric, I don't know, it's acid conjugate base. Does that make sense? So this has a -3 charge. This has a +1 charge, so we need 3 sodiums to balance that. Okay. All right, so then we need to go back and balance this. We need 3 sodiums so that we have 3 on each side. We need 3 waters so that we have 3 oxygens on both sides. We have 3 oxygens here, 3 oxygens here, and then we also have 6 hydrogens on both sides. Okay, so what we just did was we made this very clear that for every one of these acids, for every 1 mole of acid, we need 3 moles of hydroxide. Okay, so that's why we balance that. Okay, the second thing we do is we need to find the moles of acid. So I'm going to start with this number, 0.0791 grams. And then we're going to divide by the molar mass of citric acid. So I'm just going to do a really rough estimate. If this was on my Alex homework, I would make sure that I would do this really carefully. But we're just doing an example. So I'm going to add hydrogen, so 3 hydrogens plus 6 times 12 plus 8 plus 7 times 16-ish. Let's see, did I do that right? Okay, so this gives me a molar mass of 195. And this is grams per mole. So this gives me some kind of moles. This is moles of my citric acid. Oh, 7. Okay, so I'm going to take my number, 0.0791, divided by 195. That gives me moles of a citric acid. So my moles of citric acid is 0.00040056. Okay, moles of citric acid. The third step is I need to relate moles of citric acid, that's how many moles I have, to how many moles of sodium hydroxide I need. So this is telling me for every 1 mole of citric acid, I need 3 moles of sodium hydroxide. So I can set this up as a mole-to-mole ratio. There's a few different ways. You can do a shortcut on this. We're just doing the very formal way, but if you want to just do a shortcut, that's fine. So I have this many moles. Oops. Moles of citric acid. I'm just going to citric acid, and then we're going to use our mole ratio. So for every 1 mole of citric acid, then I have 3 moles of sodium hydroxide. Okay, so we've done this before. Does that make sense? The other way you could do this is you could just be like, oh, well, I have 3 H pluses, so I'm going to need 3 hydroxide. So you could just say if you have a triprotic acid, you need to multiply your moles of acid by 3. If it's a diprotic acid, multiply by 2. If it's a monoprotic acid, there's only 1 hydrogen at the beginning, just multiply by 1. So that would be your shortcut. Does that make sense? And then you don't have to balance the equation. So as you get going, if that makes more sense to you, that's fine. Do that. If that doesn't make sense, then I would probably do the long way, just to make sure you are getting the process. Okay, so then this times 3 is 0.0012169. This is moles of sodium hydroxide now. Okay, and the last step, where are we? The last thing that we need to do is to calculate the using the concentration. So we're going to use this equation. The volume equals moles divided by concentration. So we just figured out moles of sodium hydroxide. Moles of sodium hydroxide divided by concentration. They're always going to give us that. So it's 0.1800. And this is moles. And this is moles per liter. So moles cancels. We end up with liters. So divided by 0.18. So this gives me 0.00676 liters. Alex is probably going to ask you for this in milliliters, so you're going to have to convert. So how do we convert from milliliters to liters to milliliters? Divide by 1,000. That will give us a smaller number. Times by 1,000. So we're going to move the decimal. Times by 1,000, move the decimal. 1, 2, 3. So we're here. That was bad. Okay, so this gives us, and then we need to check sig figs. This has 3, this has 4, this has, oh, that doesn't count. So we've got 3. We didn't use that number. So we've got 6.76 milliliters. So that was our answer. Okay, questions on this one? No questions. Okay, the rest of the time is yours to work. Make sure you're working on Alex chapter 9. It is due tonight. Make sure you do lab 10. And then if you're all done, do the pre-lab for lab 12.